Oh my god! This is the last part. Part 7. This is also the last lesson, which is titled Linear Regression Analysis. Don't cry, but celebrate the end of the course. After today's lesson, we will know how to build the economic models. Let's start. At the beginning, several assumptions. The first assumption is we know all values of the variable y, y1, y2, and so on up to yn. We also know all values of the variable x, x1, x2, the last value is xn. The second assumption, we also know that x affects y. In other words, x has an influence on y. X is a cause, y is an effect. We can describe this relationship by a function. Y is a function of x. If we know the values of x, we can determine the values of y. This function may have a linear form, like here. Here we have a linear equation. This is the example of simply economic model, in which we have xi, a determinant of y, of course. X determines the values of y. X is called independent or exogenous variable. Y is called dependent or endogenous variable because, as I said before, x has an influence on y. It also means that y is dependent on x. In this simply economic model, we have two parameters, alpha and beta. The craft of the economic modeling is to find these unknown parameters of the equation based on the statistical data. We have the statistical series of x and y, and on the basis of this information we are looking for unknown a and alpha and beta parameters. We have to estimate these parameters using some mathematical methods. The model is the simplification of the reality. Let's imagine that x is an income and y is consumption. Of course, income determines the level of consumption, not the other way around. Yeah? We can't describe this relationship in that side. Yeah? X, income determine the level of consumption, not inversely. Okay, so income has an influence on the level of consumption. This is the simplification of the reality because we assume that the only factor that has an influence on consumption is income. is the only factor that has an influence of the consumption. So this is the simplification of the reality, because we know that many factors may have an influence on consumption. Yeah, like the price level, like supply of consumer goods, and etc. Yeah. These unknown factors were not included in the model, so we talk here about the simplification of the reality. This is our first economic model, and we are going to learn how to estimate, how to find unknown alpha and beta parameters based on statistical data. Alright, our main quest is to find the unknown parameters of the straight line, alpha and beta, that will ensure the best fit of the straight line to the empirical data. Here we have a simple graph which shows us empirical values of x and at the same time empirical, really observed values of y. For example, here the first object is characterized by x1 value, and at the same value, the same object is described by y1 value. Okay, and as you can perceive, we can see here a positively correlated relationship between the variable x and variable y values. We also know that x is a cause, y is an effect. Yeah, because we are talking about the linear relationship between x and y. X affects y, has an influence on y. And now we will try to find the straight, in other words, a model that will most accurately describe the relationship between variable x and variable y. Of course, I can turn into a draftman and draw a straight like here, yeah, and in my opinion this straight is best fitted to the empirical data. Okay, but I can ask another draftman to draw his own straight, yeah, and this next draftman will draw a straight in that way. Okay, so it's not objective criterion, yeah. I need a objective tool which will help me in finding alpha and beta parameters. As you can see, here we have infinity numbers of different straight lines. Yeah, infinity number of straight lines. Alpha parameter is responsible for the position of the straight line. The higher alpha means the higher position of the straight. It is also called the intercept. Beta parameters, in turn, is responsible for the slope of the straight. Positive beta parameter means an increasing straight line, Negative beta parameters. Negative beta parameter means decreasing straight line. It is also called a slope or gradient, yeah, because in trigonometry frames, this slope of the line is related to its angle of incline. Yeah, like here we have gamma. I need different marker. Yeah, gamma. So beta parameter is a tangent of the angle of incline gamma. Alright, but being a drawman is not a scientific approach. I need an objective criterion, and nobody says that my method is wrong, is unreal, it's kind of magic. I need an objective mathematical tool which will help me in finding unknown alpha and beta parameters, which will help me in alpha and beta parameters estimation. One of the methods of the estimation is called ordinary least squares method. Few words about the procedure of this method. Look here. Here we have the graph known from the previous slide, in which stars represent empirical values of x, and at the same time empirical, really observed values of y. In the first step, we can draw a hypothetical straight line. One hypothetical straight line, because we know that there are infinitely many of them. In the first step, we take one hypothetical straight, right? It's okay. We can draw this is our starting point, so I can draw one hypothetical straight line that represents the first version of the model. Yeah, this line represents the linear relationship between x and y. It's okay. And now, for any x observation, yeah, we can indicate empirical observation of y, and also if I have here a theoretical straight, hypothetical straight that represents the model, I can also, for each of x, I can also indicate the theoretical value of y with a roof. This is theoretical value of y. What does it mean, theoretical? Theoretical means the value that lies on the hypothetical straight. For example, we consider first object, which is characterized by x value equal to x1. At the same time, we have observed the value of y at the level of y1. This is the real empirical value of y1. And I can also indicate the theoretical value of y1. Yeah, it lies exactly on the straight line. Alright, this is the first step. We can designate empirical values of y and theoretical values of y. As you can notice, we have no theoretical values of x because x is the independent variable. Yeah? And theoretical values characterize characterize dependent variable only. Okay, this is the first step. The second step is to compute the deviations. Deviations of what? Deviations of empirical values from the theoretical ones. In first example, we have the deviation between empirical value of y1 and corresponding to it theoretical value of y1 with a roof. Yeah, theoretical means value with a roof. This is the difference. Here we have this difference between empirical y1 and theoretical y1. Here we have the deviations of the observed values of the variable y from the theoretical values of the variable y. Yeah? Here we have the deviations. And after that we raise these deviations to the second power. Yeah? We compute squares of those deviations. And we, of course, receive squares. Here we have cave deviation, and we compute a square of this deviation. Yeah? And here we have squared deviation of a k empirical value of y and k theoretical value of y. And here we have the last deviation. This deviation here is negative, but of course square is always equal to 0 and higher. Here we have the last deviation. And the next step is to, as you can see here, is to sum up all the squares. So we combine all squares together. Yeah, we can add any squares here. We compute the sum of squared deviations. And now the quintessence of ordinary least squares method. We are looking for such alpha and beta parameter that ensure the smallest sum of those squared deviations. We have to solve the mathematical problem, which is the minimalization of the function which has two variables, alpha and beta. Function with two variables, alpha and beta, and we are trying to minimize this function. Alright, it means that we need to know some advanced mathematics. The problem is more complicated than it seems. Of course, I could show you the solution, but it's not necessary. Please trust me or check it in the literature that alpha and beta parameter that ensure the best fit, the best match of the straight line of the model to the empirical data is following. Beta equal to covariance between values of x and values of y divided by the variance of x. Beta parameter is also called slope of or gradient of the straight, the interpretation is the following. Its variables y sensitivity to changes in the value of the variable x. Yeah, the sensitivity, yeah, because it is placed beside the x. Yeah, so this is the variable's y sensitivity to changes in the value of the variable x. And here we have alpha parameter. Let's remind yourself the features, the properties of arithmetic mean. Alpha parameter is equal to mean y minus beta parameter multiplied by mean x. Alpha parameter is also called the intercept. It's the level of the variable y at the zero value of the variable x. Here we have the variable x. If xi is equal to 0, yeah, 0, then y1 with a roof, a theoretical value of y, the value that lies exactly on the straight line, is equal to alpha in that situation. Okay, so this is the end of the procedure. After the estimation, we finally receive the values of alpha and beta parameters, and we can write down the equation of the model using yi with a roof, because alpha and beta parameters at this stage are known, yeah, and we have also xi value without any roofs, because this is the independent variable. And at the end of the theoretical content, some practice. Here we have a graph which is the x and y value scatter plot. It shows at the same time the values of x and corresponding to them values of y. And here we have the solution, a linear regression model in which alpha and beta were computed based on ordinary least squares method. Of course, I used Excel spreadsheet here, but you must know that Excel performs on the basis of ordinary least squares method that I have presented. Here we have alpha parameter, which is mean y minus beta x mean. Here we have beta parameter, which is covariance between x and y values divided by the variance of x. This is beta parameter because it stands beside the variable x. Alright, so let's do some tasks. Alright, let's do task 1 with a practical dimension. Perhaps, as future managers, you will face such problems. The table below contains the values of variable y, which is called total cost expressed in $1 million, and variable x, which is production volume in 1,000 pieces, observed in one manufacturing company, Business and Finance Management Corporation. And let's try to build our first economic model, the model of total costs. What do you think about the relationship that connects production volume and total costs? From the microeconomics theory, we know that production volume implies the total costs. Yeah? Production value has an influence on the total costs. So that we know the linear relationship that may connect both variables. Y1 is dependent variable. It depends on x. Y1 alpha plus beta xi. Yeah, x is exogenous independent variable. Y is dependent variable because we know from the theory that x affects y, not inversely. Okay, so we know the relationship, and the first command is to estimate and interpret alpha and beta parameters of a linear regression in the form of yi equal to alpha plus beta xi. Okay, here we have the graph that presents the data from the table. Yeah. Of course, we can perceive a positively correlated relationship, a positive linear relationship that is associated with x and y values, and we have to find unknown parameters of this kind of straight line that ensure the best fit to the empirical data. In order to find beta and alpha parameter, we should compute first. Beta is the ratio between covariance between x and y values divided by the variance of x. Here we have the covariance between the production volume and total costs. And here we have the variance of production volume. Yeah? And alpha is arithmetic mean of the total costs minus beta parameter, the average level of production. Let's start with these both simple categories. Let's compute average value of total costs and average value of production. Here we have our table. Let's sum up the values in those columns. We sum up 15 plus 16 and etc. All right, and the final result is 106.5. We sum up the values from the column of x, and the final result is 13.5. And now we are able to compute mean values. We divide 106.5 by 6 and we receive $17.75 million This is the average level of total costs based on 6 observations. And here we are able to compute average level of production, which is 13.5 divided by 6 is 2.25 thousand pieces. This is the average level of production in the manufacturing company Business and Finance Management Corporation. All right. And the next step will be computation of the covariance. As you know, covariance between the values of x and the values of y can be marked by the formula. We can use a transformed version of our formula, which is the sum from I equal 1 up to 6 of the product xi, yi, yeah? The sum from I equal 1 up to 6 of the products between the values of x and the values of y divided by n minus arithmetic mean of x multiplied by arithmetic mean of y. As you expect, the first column that we will try to build is the product between xi and yi, because here we have mentioned before product. In the first row we have 0.5 multiplied by 15. It gives us 7.5. Here we have 16 by 1.5. 1.5. It is 24. Here we have 36. Here we have, okay, I need a cheat sheet. 63, 48.75, and 70. Yeah? We know all the products. We can sum up all the products, and the sum of this column is equal to 249.25. Okay, and the mean product of the values of x and the values of y, the mean product of the values of total costs and the production volumes is around 41.542. Okay, now we have all the information that is needed to compute variance. Here we have the mean product between x and y values. 41 point, of course, around. We are talking about the around amounts. 542 minus what? 17.75 multiplied by 2.25. Yeah, because x is 2.25 and y mean y is 17.75. Of course, we can change here places, yes, because we multiply. And finally, we will receive covariance equal to 1.704. 1.604. What does it mean? It means that in general, high in bracket low production volumes imply covariance is positive. So we start with high, low, total costs. Yeah, we have a positive interdependence between the values. We know also that x implies the values of y. Yeah, the production value is a cause. Total cost is an effect, are an effect. Yeah. So in general, high production volumes imply high total costs, or low production volumes imply low total costs. As you can see here, low production volume implies low total costs, and high production level implies high total costs. Okay, we know the covariance. It's the right time to compute the variance of production volume. The variance of production volume. We need the formula for the variance of production volume. Okay, I have some space. The variance of x can be denoted by the formula. Let's remind yourself the topic of classical measures of dispersion. We can write the formula for variance using both versions, and the second version is the sum from I equal 1 up to 6 of squared values of x divided by n. So this is the average squared value of x minus min x squared. Okay, we construct the next column. The title of this column is xi squared, and we calculate squares of the values of x. And here we have the following squares. Of course, 0.25, 2.25, 4, 12.25, 6.25, and at the bottom 12.25. And the sum of all squares is 37.25, and the average square of production volume, is 37.25 divided by 6. It's around 6.208. Okay, and we now we are able to compute the variance of x. The average square was around 6.208 minus 2.25. This is the average production volume squared. And the final result is 1.146. Yeah, 6. The unit of variance of x is 1000 pieces squared. 1000 pieces squared. On the margin, the unit of covariance is 1000 pieces multiplied by $1,000,000. Alright, let's move on to beta parameter estimation. Beta parameter is a ratio between covariance between x and y values and variance of x. Covariance between the production volume and total costs is 1.604, and the variance of production volume is 1.146. So beta parameter is equal around to 1.4. Very nice parameter. Okay, few words about the interpretation of this parameter. The interpretation is following. If the production volume increases or decreases by 1000 pieces, then total costs increase or decrease by $1.4 million. $1.4 million. We can write the same thing using appropriate symbols. If xi increase or decrease by 1000 pieces, then total costs decrease by $1.4 million. Yeah? Beta parameter is positive. We have the positive relationship between the variables. So if one variable increases, the second variable increases as well. We have the positive correlation between both variables. So if one variable decreases, the second variable decreases as well. Yeah? Beta parameter is positive, covariance is positive. It means that if one variable decreases, in bracket increases, the second variable decreases in bracket increases. Yeah, so the changes occur here in the same direction. Yeah, the changes appear here with the same direction. Increases, increases, decreases, decreases. Remember that if we have beta parameter positive, it has sense, of course, because if I increase the production value, yeah, I must pay higher total costs. Yeah. All right. And the next parameter is alpha parameter. Alpha parameter is arithmetic mean of total costs minus beta parameter multiplied by average production volume. So it is 17.75 minus beta parameter 1.4 multiplied by 2.25, and the result is 14.6. 14.6. What does it mean? What does it mean? It means that this is the total costs level or the level of total costs with zero production, or the level of total costs if the production value is equal to 0. Yeah. So yi is equal alpha if production level is equal to 0, of course. Yeah. So in the in microeconomics theory, alpha parameter is actually can be treated as fixed cost, of course. No production, yeah, but we still have some costs called fixed costs. Okay. All right. And finally, we can write the linear relationship that characterizes volume of production and total costs by the formula yi with a roof, yeah, because we have estimated the parameters, now they are known, equal to 14.6 plus 1.4 xi. Yeah, this is the total costs model, our first economic model. This linear relationship express the relationship between the production volume and the total costs. Finally, we have created a handy tool that can help the management board answer a few questions. Here we have our model, the model of total costs. here we have the empirical data. We can visualize our model using the linear relationship. We know the parameters. So let's draw a straight line on this graph. 14.6 is the intercept. This is the cross point of our model, and y-axis, vertical axis. So here we have the value of 14.6. 14.6. Yeah, and we know that our straight line is increasing, so we can write the model like here. It is our model of the total costs. And now we are able to answer some questions. The management plans to increase the production volume to a level of 5,000 pieces. On the basis of this information, this kind of level of production has never been seen before. Yeah, maybe we have good times, prosperity. Firm has a potential to increase the production. The demand for the products of the company is satisfying, so we can increase the production to the level of 5,000 pieces. Yeah, but at this stage we don't know the costs, the total cost that is associated, the total costs that are associated with the level of production 5,000 pieces. Yeah, but on the basis on this model, yeah, we can predict in advance how the total costs will be if the production volume is 5,000 pieces. Yeah, forecasting. So now we are playing a role of financial analysts. Let's answer this question. Production volume at the level of 5,000 pieces. So my production value is 5,000 pieces. I assume that the level of production is 5,000 pieces. And on the basis of the model, I will answer the question, how high will total costs be? Yeah, it's very simple. I will use the linear equation. Here we have our independent variable. Our model pulls 5, is taking 5 here, yeah? So I have 14.6 plus 1.4 multiplied by 5, yeah? 5 is exogenous variable. Xi is an exogenous variable, so I ask the model about the total cost level if I take any production volume from 0 to the infinity. And this level will be, okay, I will use a calculator. Wait a second. Oh my god, it's very hard to open. Alright. So 1.4 multiplied by 5, it's 7, plus 14 and 6 is of course $21.6 million. Yeah, so we can answer the question of the management board. How high will total cost be if production volume will reach 5,000 pieces? And we, as financial analysts, answer that in that situation we will reach the level of total costs $21.6 million. Alright, we have the next question, the next event. After increasing production to the level of 5,000 pieces, there is still the potential to increase production by 5,000 units pieces. How much will total cost change if production volume will increase by 5,000 pieces? Okay, let's remind yourselves what I said before when I talked about the beta parameter interpretation. If production volume increase or decrease by 1,000 units or pieces, then total costs increase or decrease. Yes, we have the same direction because we have a positive correlation between the variables by $1.4 million. Okay, and now we are able to answer the question. Production volume will increase by 5,000 pieces. Production volume increases by 5,000 units pieces. Then what will happen with the total costs? The rise of the total costs is proportional. Yeah, if I have 1,000 units, I have $1.4 million increase. So when I have 5,000 units, then I have increased by $0.7 million. Yeah, $0.7 million. The rise here is proportional. Alright, we can summarize the information that we have gained from the model. The first information is a kind of forecasting, prediction of expected level of dependent variable if I take a certain value of independent variable. Like here, I took 5,000 pieces and I received the expected value of total costs. The second information is about the changes in the dependent variable if I change the values of the independent variable. The interpretation of beta parameter. Like here, if I change independent variable by a certain amount of units, what will happen with my dependent variable? Changes. Yeah. And the third information, very important information, is interpretation of alpha parameter. Yes, here alpha parameter takes the form of fixed cost. Yeah. So this is the level of dependent, yeah, the level of dependent variable. If I set the level of independent variable to 0, is the level of dependent variable if independent variable is equal to 0. Is the level of endogenous variable if I set the level of exogenous variable to 0. Okay, 3 informations. And the last one, the last command, compute and interpret correlation coefficient and R² for these two variables. Yeah, so the previous part. As you remember, coefficient of correlation is given by the formula covariance between x and y values divided by the product of standard deviations. Yeah, we know the covariance. It's easy to indicate the standard deviation of production value, because we had a variance of x at the level of 1.146. Yes, so it's easy to find standard deviation of x on the basis of variance of x, and the only thing that we don't have is standard deviation of total costs. Yes, so we need the column of yi². Yeah, yi². And we have quickly 2, 2, 5. Yes, I raise this column to the second power. 2, 5, 6, 3, 2, 4, 3, 2, 4, 3, 8, 0, 25, and 400. The sum is 1909.25, and the partial result, the average square of total costs, 8. Let's check it out at home. Yeah, and on the basis of this information, please try to compute the variance and standard deviation of total costs. Now I'm going to move to the immediately to the value of coefficient of correlation, which is 0.845. What does it mean? It means that between both variables, production value and total costs, we observe a positive, very strong correlation. And how about R² coefficient here? R² coefficient is equal to 0.714. It's very important coefficient here. Yes, because it determines the degree of the fit, of the match of the model to the empirical data. Yeah, it's a kind of measure that measure the match, the fit to the empirical data. The higher R squared, the better fit of the model to the empirical data. And now we have the information that the variability of production volume explains the variability of total costs in around 71%. Yeah? So the degree of the match of the model to the empirical data is quite satisfying. Yeah? We have explained 71% of the variability of total costs by the variability of production volume. Other example, task 2. Below you will find data about the demand in tons. This is variable y, and the price level, variable x, expressed in euros per kilogram on one specific good, which is pork. Please try to build demand model for a pork on the basis of the statistical data. Alright. It seems to me that you remember the law of demand from the microeconomics theory. The higher price means the lower demand, or the lower price means the higher demand. We expect here a negative sloped linear relationship between the price and the demand. And of course, price is a factor of the demand. Price of the pork implies the level of the demand, not inversely. Yeah? X affects Y here. Alright, we will try to build the model in the following form: yi equal to alpha plus beta xi. As you remember, the first step in building a model is to find beta parameter, which is a coefficient, a ratio between covariance between the values of both variables divided by the variance of the independent variable. Here we have the graph that presents the data from the table, and as we have expected, here we are looking for alpha and beta parameters of the straight line that ensure the best fit to the empirical data, and of course we can perceive a negative relationship between both variables. It means that the higher price, the lower demand, and the lower price, the higher demand for a specific good. We analyze demand of pork and demand of Sorry, I have a call. Alright, we analyze demand for a pork and its price. Yeah. First of all, we need to fill the gaps in the left side of the table. The sum of the values of the demand is 45.1 and mean level of the demand for a pork was 9.02. Yeah, we have 5 observations and mean level, average level of pork demand, it was 9.02 tons. And here we have the price level. The sum of all prices is 15.7 and the average price for a pork was 3.14 euros per kilogram. Covariance between the demand and the price can be denoted by the sum from I equal 1 up to 5 because we have 5 observations. The sum of the products between the sum of the products of the demand and the price divided by n minus 2 arithmetic means. Arithmetic mean of x and arithmetic mean of y. And here we need the next column titled xi multiplied by yi. 10.3 by 2 is 20.6, 24.5, 18.05, 38.4, 33.75. The sum of whole column is 135.3, and the average product of the demand and the price level is 27.06. So now we are able to compute the covariance. 27.06 minus 902 multiplied by 3.14. And covariance here is equal to minus 1, 2, 6, 3. Almost. Okay, so it's negative. It means that we are talking about the negative relationship between the price level and the demand. So it means that in general, higher, in bracket lower, higher price level means lower demand for a pork. Yeah? In general, higher, in bracket, lower price level means lower, in bracket, higher demand for a pork. Yeah, higher price, lower demand. Lower price, higher demand. Okay, variance of the price level. We need the column of squared values of x. 2 squared is 4. Here we have also 6.25, 3.61, 23.04, and 20.25, the sum of squared values is 57.15, and average square of the price level is 11.43. And then we can compute the variance of x, which is the sum of squared values of price divided by n minus mean squared mean value of x. In our example, 11.43 minus 3.14 squared gives us approximately 1.570. Of course, the unit of this measure is euros per kilogram squared, and on the margin the unit of covariance is euros per kilogram multiplied by tons. Yeah, it has no sense, but it doesn't matter. Okay, let's compute beta parameter of the linear regression. Beta parameter of the linear regression. Beta parameter is a ratio between the covariance and variance. In our example, minus 1.263 divided by 1.57. It gives us the value of beta minus 0.804. What does it mean? If pork price xi increase or decrease by 1 euros per kilogram, then demand for a pork increase, decrease, increase, yes, by 0.804 tons. Yeah, we have different directions of change. If price increases, the demand decreases. If price decreases, the demand increases. All right. And after that, we can give as a market analyst the value of alpha parameter in the demand model. This is y mean minus beta x mean. Y mean is 9.02 minus beta minus 0.804. Watch out, minus and minus, multiplied by 3.14, and the approximation of the result is 11.545. 11.545. Yes, minus and minus gives us the plus. Okay, how about the interpretation of alpha parameter? We have estimated the demand model, which has the form 11.545 minus 0.804 xi. How about the interpretation? How about the interpretation of alpha? This is the level of the demand in the situation when pork price is 0. Yes, it is the situation when pork is given for free. Yeah. The level of pork demand when price of pork is equal to 0, when pork is for free. Beta parameter can be also called sensitivity of demand to price changes. Yeah, here we see the sensitivity of the demand to the price changes. If xi price decrease by €1 per kilogram, then we observe the following changes in the demand. Okay, and now we are playing a role of market analysts. We predict that price of the pork will stabilize at the level of €5 per kilogram. What will happen with the demand for a pork? Of course, we can utilize our model, our analytics tool. So we expect that the price level stabilizes at the level of €5 per kilogram. And then what will happen with unexpected demand? Because expected, with a roof, we are talking about the values that lie exactly on this straight line. Yeah, theoretical value, expected value. The expected value will be following: 11.545 minus 0.804 multiplied by 5. Okay, where is my simple calculator? 5 multiplied by 0. I hate this calculator. I like scientific calculators. Okay, it's 4.02. 11.545 minus 4.02. It's 7.525. So let's answer this question. If price of pork, if the price of pork will stabilize at the level €5 per kilogram, the demand is equal to 7.525 tons. If the price of pork will stabilize at the level 5 euros per kilogram, the demand is equal to 7.525 tons. Try to make a plot of a model. It's very easy. Alpha parameter is our cross point of our straight and a vertical axis. Yeah? First information that we need to make a plot is that when xi is equal to 0, then yi with a rough theoretical value of the demand is 11.545. And the second question is about the cross point of our straight line and horizontal axis. Let's try to find this cross point between our model and horizontal axis. Okay, then we have the situation when the demand is equal to 0. 11.545 minus 0.804 xi. Yeah, 0.804 xi is equal to 11.545. xi is equal to wait a second, 11.545 divided by 0.804, and this level is 14.359. Yeah, so if the demand is equal to 0, then the price level is should be around 14.359. Yeah? Okay. So we can make a plot. We can make a plot like here. Okay. Of course, we assume that the demand and the price are non-negative, yeah? It has an economic sense. Here we have yi, here we have xi. We know two cross points, 11.545, and here we have the cross point established at the level of 14.359, and this is our economic model. Economic model of the demand for a pork. yi roof 11.545 minus 0.804 xi. Right. Okay, and the last one, compute and interpret R squared, yeah, for this variable. So please evaluate the degree of fit, of match of the model to the empirical data. Of course, you can try it at home, yeah, because I don't want to do the same thing for one more time. R squared coefficient here is equal to 0.871. Check it out in home. What does it mean? It means that the variability of the price explains the variability of the demand in 87%. It means that we have achieved a high degree of the match of the model to the empirical data. So our model, our parameters are very good estimated. And finally, we got the end of the course. Thanks for watching. I hope you learned something important and useful. See you at the exam. The exam will be, of course, very, very easy. Goodbye.